For this video, we're going to be talking about related rates, which is basically a problem in calculus where we're trying to describe a change in one variable by analyzing the change of another variable. So let me explain. We have this example problem here where water leaking onto a floor forms a circular pool, and the radius of the pool increases at a rate of 4 centimeters per minute. How fast is the area of the pool increasing when the radius is 5 centimeters? So, helpful thing to do first is to write down what we're given. We're given at the rate the radius increases. We're trying to find how fast the area increases, and we know the radius we're dealing with is 5 centimeters. Alright, so let's write down everything. We know the area of a circle, which is pi r squared. We know that r stands for radius. And we know that we're asking about how fast, so we're going to be talking about time, so t is going to be our time. Now what else do they give us? They give us the rate at which the radius of the pool is increasing. So the radius increases at 4 centimeters per minute. When we're talking about a rate at which something increases, we know that when we're talking about increase or decrease, we're talking about the derivative. So the derivative of the radius with respect to time is equal to 4 centimeters per minute. So that's the rate over time at which the radius is increasing. And we're trying to find how fast the area of the pool is increasing. So we're trying to find the derivative, the change in the area with respect to time of this pool. So let's just take it step by step. Since we're trying to find the derivative of the area with respect to time, let's take the derivative of this equation with respect to time. So we have a equals pi r squared. So we're going to take the derivative with respect to time on both sides. The derivative of a with respect to time is pi r squared. The derivative of that guy with respect to time, we're going to do implicit differentiation again. So remember back in the day when we did that, so we're going to do the derivative of pi r squared is going to be 2 pi r dr over dt. Okay, so since we had to take the derivative of pi r squared with respect to time, we had to do implicit differentiation. So now we got the derivative of the area with respect to time equals 2 pi r dr over dt. So what was dr over dt? That was the rate at which the radius was increasing or decreasing. And we know that the radius increased with 4 centimeters per minute, which was our dr dt. So now we can plug this in for this. So we have dA dt equals 2 pi r times 4, which in this case is 8 pi times r. Now we're still trying to find how fast is the area of the pool increasing when the radius is 5. So this is where the radius comes into play. So we're going to plug that into our radius. Which equals 40 pi. And we're talking about the rate area increases. So it's going to be centimeters squared per minute. For this problem, we're dealing with an observer watching a rocket blast off from a launch pad. So let's first draw what we see. We know that the observer stands 700 feet away from the launch pad. And then we know that the rocket blasts off and maintains velocity of 900 feet per second. So we can assume it's going to be going up 900 feet per second. And we don't know how fast the observer to rocket distance changing when the rocket is 2,400 feet from the ground. So we know after it takes off, the rocket's going to be up there somewhere. We're trying to figure out that distance. So let's try and figure out what we know. Well, we know how to find x. Let me just get a pen here. So we got x squared equals 700 squared plus whatever the altitude is. Okay, so that's going to give us our value for x, no matter what. We know that the rocket is going at a velocity of 900 feet per second. So that means the derivative of the change in the altitude over the change of time is equal to 900 feet per second. Okay, velocity was the change in position over change in time. In this case, the change in position is dealing with altitude. And what else do we know? We're trying to find the change in the distance from the observer to the rocket. So that means we're trying to find the change in x. So that means the derivative of x with respect to time is what we're trying to find. So let's start with our equation. We have x squared. I'm going to start over here to give myself a little room. We have x squared equals 700 squared, which is 490,000. And since we're trying to find dx dt, let's take the derivative of both sides with respect to t. The derivative of x squared with respect to t is 2x dx dt using implicit differentiation. The derivative of 490,000 is 0. And we have 2a d over dt. So just solving for dx over dt, we get a over x times dA over dt, which is 900 feet per second. And we're asking about how fast is the observer to rocket distance changing when the rocket is 2,400 feet above the ground. So that means our altitude is going to be 2,400. Now, what are we going to do for this x? Okay, so this x is going to equal the square root of 700 squared, which is 490,000, plus the altitude. Well, we know at this moment our altitude's 2,400. Okay, so whatever that turns out to be, which is 6,250,000. Take the square root of that, we get 2,500. So when the altitude is 2,400, we know the distance from the observer to the rocket is 2,500. Now, the rate at which that is changing at that time is equal to 2,400 times 900 divided by 2,500, which in this case is 864 feet per second. Okay, after watching this video, you should be able to try these problems, or just a singular problem. It's dealing with the change of the area of a spill increasing, and we're trying to find the rate at which the radius is increasing. It's very similar to the first problem. Okay, see you in class.